Today we're going to present about evolution assessment by modeling and computer analysis. This is our group members. We have our advisor named Inchi Zakaria, followed by director Sarvesh, and assistant director is ADLI, and secretary is Deva. We have three engineers. First engineer is IZZAT, and second is HANAFI, and third is HABIBULLAH. This is our company design, and our company name is Arch Design. Our mission is Arch Design to provide client-focused service through our responsible practice of engineer and surgical design. And our vision is to be respected surgical design firm, providing high quality design and service to our client with honestly and integrity.
My name is Muhammad Hanafi bin Rahim. My mention number is 132310146. And today I going to present about introduction and background theory. For the project title is Prototype V12 Engine, M120 V12 Engine Design. For the objective of the project is reverse engineering, develop refine the prototype V12 engine, specifically the M120 V12 design, with a focus enhanced design type, material use, and simplification process and value improvement. Okay, for the scope of the project focus is enhance the M120 V12 engine prototype by reverse engineering, improving design, optimizing materials, simplifying process, validating performance, and ensuring cost effectiveness and regulatory compliance. For the problem statement is the current M120 V12 engine prototype face challenges related and outdated design, suboptimal materials, complex manufacturing process, and limited performance efficiency.
My name is Muhammad Izzat Farhan bin AZIMAN. My metric number is B1323100047. Next is explanation of the product. Overview the product. The project prototype V12 engine M120 V12 engine design aims to revolutionize automotive engineering by reverse engineering, developing and refining the existing V12 engine prototype. Focus on enhancing design, optimizing materials, simplifying manufacturing processes, and implementing valid improvement. The project strives for a cutting-edge engine that excels in performance and efficiency. Function of the product. The primary function of the prototype V12 engine M120 V12 engine design is to serve a high performance and efficient power source for automotive applications. The refined V12 engine is intended to propel vehicles with enhanced power, reliability, and efficiency.
Rahim, my name is MAZLAN. Actually, right here, I will present about the chapter 2, the rough sketch about our project. First, we have the rough sketch of our hand drawing, and here we have front view, side view. Next, right here we have the review and upper view for our sketch, simple sketch. And right here we have a sketch ticket. Okay. This sketch is a little bit hard because I need to build part by part in assembly. And right now we have not actually sketch, actually the actual product actually. But on the sketch we create the actual product. Okay.
Greetings. For our Katia project, we have decided to do the M120 V12 engine, which is based on or inspired by the Mercedes-Benz W140 S-Class. So this engine is a V12 engine with a engine of 6 liter. It's a 6.0 cc V12 engine. So in the development process for our drawing, translating all that drawing into CATIA, we had to do reverse engineering, which is by researching and surveying the engine type and by collecting data based on the specifications. So this is mainly about the engine measurements, engine type, engine sizes, the materials that were used, how we can simplify the drawing, and how can we also improve some design and also make it simpler at the same time. So this was done, and one of the main things that we learned during our reverse engineering research process is by understanding the material that was used, which is aluminium. Aluminium is a very light and strong metal, so it was used in casting or creating that engine block, engine head, piston head, cylinders, valves, and most components.
Okay, for chapter 2 for development process, chapter 3, sorry, development process, which will about the part. Here we have the cylinder, which coding the code is AD004. Its volume 0.01 and 3, and the area is 2.264 and 2. With weight, the mass is 11.32 kilo. The density is 100,000 gram and 3. Okay, so next we have here the cylinder head. The cylinder head right here is volume 0.04 and 3, area 1.677 and 2. Mass is 3.57 kilogram. With density is 1000 kilogram and 3. The 1000 gram and 3. Okay, for cylinder head is put by AD005 cylinder head. Right now is AD007 piston. Is 1.5 3 E 0, 4 and 3 for the volume. For the area is 0.04 and 2. For the mass is 0.416 kilogram. And density is 2,710 kilogram and 3. Okay, for crankshaft. Okay, right now crankshaft is for the volume is 0.02 and 3. For the area is 0.341 and 2. For the mass is 0.572 kilogram. And for the density is 2,710 kilogram and 3. Okay. For the code is AD012 crankshaft, and the component material is white steel. Okay, steel.
Assalamualaikum warahmatullahi wabarakatuh. So my name is Muhammad AZMI. Okay, I will explain about assembly for cylinder block. Firstly, I will do the piston set, which connect between piston with piston bit. After that, I will do conrod set, which connect between conrod with conrod connection, and I will open the new product assembly. I will input the cylinder block, and I will connect the cylinder block with a crankshaft. After that, I will put the crankshaft connection and attach to the cylinder block. After that, I will put all the conrod set with the third mount 12 and connect to the crankshaft. After I connect the conrod, I will put lastly with the piston set to the each cylinder block. So the complete assembly will be like the picture lah. Okay, next, I will explain about assembly for cylinder head. Okay, the first thing I will do is attach the valve for the intake and valve for exhaust into the cylinder head. After that, I will put uh, each uh, each inlet with a fuel injection, which is the third mount with 12. After that, I will put two spark plug uh, into the each uh, cylinder head and after I done the internal cylinder head, I will put the plate or we call a gasket for the manifold for exhaust and the manifold for intake. And I will attach the exhaust pipe and the intake pipe. And lastly, I will put the camshaft with, in their place, and I will connect using a constraint, which is cylinder constraint and the contact constraint. So the final result, which is like the picture lah. So this picture will uh, create by the explode view. Okay, that's all.
So for the discussion, the intake and exhaust valves had undergone static analysis with distributed force in an increasing manner. We have decided to do an analysis, which is a static analysis with distributed force on the intake and exhaust valves. So we understand or we know that the valve is a constantly moving component. In an engine, the valve has to open and close all the time or every time during the intake stroke or the exhaust stroke. So during this, we wanted or we decided that the valve will be the simplest study for us to do an analysis on, because in the combustion chamber, it has to withstand all that force, all that heat, and all that extra moment, that all that energy that is inside the combustion chamber. So the valve has to be built and designed very accurately and very carefully, because although it looks like a very small simple component, it plays a major part. So the valve tip is used as a clamp, as you can see in this photo here, and the distributed force is applied on the valve face or the valve head to study the structural strength of the valve. So when the force is applied, it acts from the face all the way to the tip of the valve, compressing and deforming the valve body to measure, study, and calculate the required data, mainly the von Mises stress. So the analysis was done with an applied load in an increasing manner. So for the first one, we decided to do 1 kilonewton of force. So 1 kilonewton of force acting on the valve head. So based on this von Mises stress data or graph, we can see that this valve can withstand a great amount of force and stress. So this makes it somewhat, or in a good term, structurally strong and good. As you can see here, the lowest or the safest is at 5.2 times 10 power 6 Newton per meter square of stress. And based on our analysis, it has proven that it can withstand it to a great amount. It is good. And the maximum amount of von Mises stress that has been tested is 5.85 times 10 power 7 Newton per meter square. So the material that was used for this analysis, or this valve, is aluminium with a Young's modulus of 7 times 10 power 10 Newton per meter square, Poisson ratio of 0.346, density of 2710 kg per meter cube, coefficient of thermal expansion with 2.36 times 10 negative 5 Kelvin degrees and with a yield strength of 9.5 times 10 power 7 Newton per meter square. So we have studied an analysis on the intake valve. So we know that the material is used, which is aluminium, and a density of 2710. Aluminium is light, it is strong, and it is structurally very rigid. So this analysis uses multiple tetrahedron squares, which basically maps each component or each part, each surface of this valve to study the acting loads on them. So the von Mises stress has been analyzed and the data have been stated in the discussion. Increasing loads of 1 kilonewton, 5 kilonewton, 10 kilonewton, 15 kilonewton, and 13 kilonewton have been studied. These are average or estimated values on a real world scenario or a real world working engine condition. So these are the ranges of energy or the forces that may be used, and 15, 10, 15, and 13 kilonewtons were measurement data or distributed force that were used to push to see the limit and capability of this intake valve. We did it in an increasing manner from 1, 5, 10, 15, and 30 to see the breaking point or the amount of force that this valve or the stress that this valve can handle. So for the factor of safety, which uses the formula ultimate stress and actual stress, we have studied based on the data of each analysis that was done from 1 kilonewton all the way to 30 kilonewton. For this, for 1 kilonewton, factor of safety is 1.624. For 5 kilonewton, 0.3, 10 kilonewton is 0.162, 15 kilonewton is 0.108, 30 kilonewton is 0.054. So based on our analysis and the study that has been done, factor of safety for 1 kilonewton is the best because this valve has a factor of safety which is 1.624. And this applied value is reasonable and strong enough for the valve to stay rigid and take in all that energy that is produced and done during an actual or a real world scenario. Besides the intake valve, we did an analysis for multiple other components, which has been the piston head, connecting rod, camshaft, crankshafts, even the connecting rod endpoints. So this analysis was not limited to static analysis. I also went to the depth to do thermal analysis and moment analysis. So we know that, for example, this valve has to withstand all that heat during combustion. So it has to be able or to be designed in a way for it to dissipate and handle the heat that is being produced while also maintaining peak performance and peak function. So this analysis, which is the thermal analysis, static analysis, and moment analysis, was done for the connecting rod, and an example of moment was done on the camshaft because we understand that the camshaft is constantly rotating. So in that rotation, there is somewhat of a friction, and there is moment where force is being used or being created in a direction. So that was also done to see the capability and the strength of these components that were done. So here is an analysis that was done on the intake valve. So as you can see here, the valve tip has been used as a restraint and the distributed force is applied below, as you can see in the video. So here is a process of compression to see the amount of distributed force that the valve can take, or an analysis that was done on the structural part of the valve when force was applied to it. Apart from the intake valve, I also did an analysis on the piston head, which also involves static analysis and thermal analysis. So as you can see, the applied force is acted on the piston head, the top of the piston head, because that is where combustion happens. So that piston is constantly going up and down, and in that motion, combustion happens in this area. And as a restraint, I have used the center point or the holding point between the piston, where the piston head will be connected to the connecting rod through a piston pin. So that actually works as the restraint or the constraint to this, and the force acts on the piston head. And as you can see here, the piston's structural integrity has been studied and the data has been shown in the report. Not only that, I also did an analysis on the piston pin, which acts as the connection point between the piston head and the connecting rod. So the sides of the piston has been used as a restraint, and force is applied on top of it, simulating a real world condition of the piston. So here is one Miser stress, but applied on a different level. As you can see here, the colors prove that this piston pin is able to withstand the amount of force that has been applied, which is marked as the dark blue and light blue areas, which confirms the structural integrity of this piston pin. A thermal analysis was also done, and based on this data, it shows that during the expansion, or when the piston pin is pushed to its maximum limits, thermal analysis of 420 Kelvin, which is an average working temperature or working condition of the piston pin in the real world scenario, it can be proved that the piston pin has been able to withstand all that pressure, all that stress, and all that heat, which confirms that this piston pin is eligible or can be used properly due to its functionality and its strength.
In 3D modeling is that it's able to generate precise and detailed models. CAD software offers accurate measurements and dimension, guaranteeing the accuracy of the model, unlike traditional manual methods. This high level of precision is especially valuable in intricate engineering and or architectural endeavors, where meticulous measurements and considerations of every aspect is visual. A further notable benefit of CAD software in 3D modeling is high level of efficiency. CAD software facilitates the rapid and effortless creation and modifications of 3D models by design and engineers. In addition, CAD software offers the multiply of capabilities that improve the design process, including simulations and analysis tools.